Assalamu alaikum and good morning, everyone. So today we're going to continue with mass spectrometer, which is another analytical technique that we are looking at topic 22. So earlier on, I've introduced the concept of molecular ion to you. Basically, molecular ion is when the molecule that you introduce into the mass spectrometer is being bombarded with high energy electrons and one of its electron is being kicked out. So when a molecule loses one electron, it becomes a cation, and we call this the M+ molecular ion. When you introduce a sample into the mass spectrometer, what happens is that the first one is the molecular ion stays intact, but one electron is being removed. Sorry, the molecule is being ionized into a molecular ion where one electron has been removed from the molecule. The second option is fragmentation, where your molecule is being broken down into smaller parts called fragments, which can be cation or neutral, which is in the form of radical. So the ones that are being detected by the detector in a mass spectrometer is the fragments or the molecular ions that are charged with positive charge. Next, we're going to look at M+1 peak. That means on top of your molecular ion, there is a +1 unit in your spectrum. Usually, molecular ion appears as the last line on your x-axis. So we say that the signal for molecular ion is the one with the biggest mass to charge ratio. We wouldn't call the molecular ion signal as the highest signal or the biggest signal because students tend to confuse this with the tallest height of the peak or the tallest height of the signal, which is not the molecular ion. So molecular ion has the biggest mass to charge ratio, which you should be looking at along the x-axis. M+1 peak, that means there is additional 1 unit to your molecular ion. So the learning objective for this section is to deduce the number of carbon atoms N in a compound using the M+1 peak and the formula N equals to 100 times abundance of M+1 over 1.1 times abundance of M+ ion. Okay, so we'll talk about that later on. Right, so if you see your molecular ion peak is not the biggest mass to charge ratio, okay, and there is another line beyond it and the difference is just by 1 unit, okay, that's why it's called M+1. This is because of the presence of carbon-13 isotope. All right, we must not forget that carbon does not only exist as carbon-12, carbon-13 is also present, okay? So I'll give you an example later on. So whenever you see there's a difference in 1 unit between these 2 final peaks towards the end of your x-axis, that means isotope carbon is present, or another isotope will be present like chlorine or bromine, which we will look at later on. Okay, so for example, here in the spectrum, I can't remember which molecule this belongs to. It looks like this peak is the molecular ion peak, the M+ peak, okay? And that is in fact the M+ peak, but if you notice that there is a smaller peak, lower relative abundance, which confirms that this M+1 is a little bit rare than your M+ molecule, because that means the isotope is probably not as abundant as your M+, okay? So I'll just label it first, M+1 and then that's M plus, right? Usually M+1 is put in a square bracket, but it doesn't matter. Okay, if you include the square bracket or not, it doesn't matter. The formula, however, you have to be careful. It's 100 over 1.1. The 1.1 is basically something to do with the abundance of your carbon-13. Times by the abundance of M+1. Now we want to use the Y values. That means values on the Y-axis, not the X values. Okay, for example, for M plus peak, the abundance is about, that looks like 85 to me. Okay, so I take 85, abundance of M+1 first. That looks like, I don't know, 3% to me. Okay, so the 3% goes here, abundance of M+1, and then the 85% goes to the bottom number. Students always think it's the X values, okay, not 59 and 58, not 59 over 58. It is the Y values. So be careful because your Y axis is your abundance. So that's the formula that you're going to use, okay? In any organic compound, there will be 1.1% carbon-13. This can help work out the number of carbon atom in a molecule by the equation given here, right? So I will just use the formula first, and then we'll talk about this M+1 later on in a mass spectrum, or graphically we say. Okay, so compound A has a molecular ions at M/E value of 120. So that means the mass to charge ratio is 120. The relative abundance is 23%. So we're interested in the relative abundance. Just label this as your molecular ion. So that's M plus, and a peak at mass to charge ratio of 1:1 with a relative abundance of 2%. So you can see the difference in abundance. One is 23%, the other one is 2%. Okay, and you notice as well, the molecular ion mass to charge ratio is your MR, 120. However, there is a +1. That's why we call it M+1 at mass to charge ratio of 1:1. Okay, so how do we use the formula for this? Is N equals to 100 over 1.1, you don't change the number, times by the abundance of M+1. So this is your M+1, 1:1. But we don't want the mass to charge ratio, we want the abundance, which is the 2%. Okay, over the abundance of M plus. The abundance of my M plus is 23%. Okay, so I just take 2 over 23. Why can't I take 2 over 100 divided by 22, 3 over 100? The percentage will cancel out. Okay, so if I do the calculation for this, over 1.1 times by 2 over 23, I should get, sorry. I should get 7.91, okay? And if I round it off to the nearest whole number, that would be 8, because number of carbon atoms in a molecule, it has to be a whole number, okay? You cannot have like 7.9 carbon in a molecule, all right? So that means this compound A has 8 carbons. The nearest whole number is 8, so there are 8 carbons in the molecule. Okay, so I don't know what else is in this molecule A, so I'm not going to bother with identifying the molecule. Right, moving on to the next question. A hydrocarbon, so here it's hydrocarbon, that means it contains hydrogen and carbon only, has a molecular ion peak at 84 with relative abundance of 62%. So I'm interested in the relative abundance, and that corresponds to M plus molecular ion. The MR, I will just label the MR of this molecule is 84. Okay, M+1 peak at mass of 85. So you can see the difference between 85 and 84 is just by 1 unit, right? So that means there is a presence of carbon isotope, carbon-13. I'll show you in the diagram later on. Okay, the relative abundance for the M+1 peak is 4.1%, and I am interested in that. That corresponds to M+1, right? Calculate the number of carbons in the hydrocarbon, hence deduce its molecular formula. The hydrocarbon does not decolorize bromine water, so that means it is not an alkene. Actually, it should be rephrased as the hydrocarbon does not decolorize bromine water in the dark. So that means it's an alkene, okay, not an alkene. Because if it was an alkene, it would react with bromine water and it decolorizes bromine water. So that's a hint that tells us whatever molecule we have identified this hydrocarbon is, it cannot have a double bond. Okay, so in order to identify the molecule, first we need to know how many carbon atoms are present in this molecule, and we can use the formula N equals to 100 over 1.1 times by the abundance of M+1 is 4.1 over the abundance of M+, which is 62. So that should come out as 6. Okay, 6.011. So it's close to 6. That means this hydrocarbon contains 6 carbon atoms. Okay, now I cannot use this formula to find the number of hydrogens. However, since I know that there are 12 carbon atoms and I know the MR of this molecule is 84, I can find the remaining mass should tell me that it belongs to hydrogen. Okay, so that means 6 carbon plus how many hydrogens, I don't know, is equals to 84, where 84 comes from here. Molecular ion peak is usually the MR of your molecule. Okay, so if I work that out, 84 minus 6 times of carbon, so that's 6 times 12, I've got hydrogen equals to 12. This is the mass of the total hydrogen. All right, since we know that hydrogen has a mass of 1, that means there must be 12 hydrogen present in this hydrocarbon. So that means formula of the hydrocarbon is C6H12, right? If you're not convinced, you can calculate 12 times 6 for the carbon and 12 times 1 for the hydrogen, sorry, 6 times 12 for the carbon and 12 times 1 for the hydrogen, and the MR should give you 84. Now, C6H12 looks like formula for alkenes, but this question already said that it is not an alkene. So that means the structure of the molecule would be an alkane, but usually alkane would have more hydrogen, right? So that means it is a cyclic alkane. Okay, so if you see this, sorry, I shouldn't have that many. 2, 4, 6. Correct. 8, 10, and 12. Okay. It doesn't contain single bond. It has 6 carbon and 12 hydrogens. And so the name of the hydrocarbon is a cyclohexane. Okay, so that answers your question. Now you may ask, what's the molecule or the species that is responsible for the formation of the peak at 85? How can you add one more unit to the mass of a cyclohexane? As mentioned earlier, that means you have an isotope of carbon, which is carbon 13. So I'm going to make this smaller. So this is the species that is responsible for the peak at 84. Okay. So if I copy that down, copy, what is the species responsible for the peak at 85? So basically it is similar except for, I'll change the color to green, okay, except that one of the carbon is carbon 13. Okay, so if I add a plus sign to it, this is the molecule that is responsible for the peak at 85 mass to charge ratio. Okay, how do I know that? Okay, let's count. I've got 13 carbon plus 12 plus 12 plus 12 plus 12 and another 12. So that means 5 of my carbons are carbon 12. 5 times 12 is 60 plus carbon 13 is 73 plus 12 hydrogen because there's no difference. So I've got 85, okay? So the reason for that one unit is this person, carbon 13. One of the carbon in the cyclohexane is made up of carbon 13 and not carbon 12. Whereas in the signal that was formed by a peak at, or a signal at 84, it is produced by a cyclohexane that is made up of all carbon 12. Okay, so I'll label that for you. Carbon 12, because carbon 12 is quite common. We don't usually write it like that, okay? Because I think everyone, it's understandable that it's just carbon 12. But in this case, since we are talking about isotopes, you can label it carbon 12, carbon 13, carbon 13, sorry, carbon 12, not carbon 13, carbon 12, carbon 12, carbon 12, as well as carbon 12. Only that one atom is made up of carbon 13. Okay, so I would label this peak at 84 mass to charge ratio. Now, how do you get that carbon 13 in the molecule? It's by chance. It's not something that I can control, because in 100 molecules of carbon, there will be about 1.1% of it made up of carbon 13. So if I'm producing molecule, the probability, the chances is also there. Okay. Right. But it's not that common. That's why the abundance is really, really small. You can see that the abundance of this molecular M+1 peak is 4.1%. Okay. And mostly majority will be the M+ peak, which is at 62%. Okay, I hope that makes sense. If you want to copy this down, I will keep it here and you can pause or screenshot. Okay, I'm moving on to the next part. So here is another example to determine the number of carbon atoms of compound X. So compound X, we're not being told that it is a hydrocarbon, and that's fine. They only want us to find the number of carbon atoms. So if you look at the molecular ion peak, okay? This is your M plus peak, and then that's at 58. At 59, that's M plus 1 peak, all right? So my guess is carbon-13 is present. So whenever you see a difference of 1 unit between the molecular ion and the M+1, that should give you a hint that carbon-13 is present. Okay, determine the number of carbon atoms of compound X with the following mass spectrum. Okay, so we use the same formula. N is equals to 100 over 1.1, abundance of M+1. So if I take a ruler, I'll take a ruler here and then I read it. That should be around, because I checked, 3%. Okay, so that is 3% of abundance, whereas the M plus peak, which is the molecular ion peak, that is actually 85%. Okay, so if I sub these numbers into the formula, it should be M+1 is 3, M plus is 85. Okay, so can you please work out the number and round it off to the nearest whole number? Okay, so and then your answer would be there are X carbon atoms present in compound X. Okay, so we don't know anything else about it, and we're not expected to find out the molecular formula or the identity of compound X, so we just leave it there. Okay, moving on to the next one. Effect of chlorine on mass spectrometer. Now, chlorine atom is another element that has isotopes. Okay, if you look at your periodic table, your chlorine atom has a mass of 35.5. Okay, so that means, since it has a decimal place, that means there must be other carbon atoms. There must be other chlorine atoms isotopes. Okay. Deduce the presence of bromine and chlorine atoms in a compound using the M+2 peak. M+2 peak gives you an idea that this peak has a difference of 2 units to your molecular ions. Okay, if it's M+1, that means the difference is 1 unit. M+2, the difference is in 2 units. And later on, you will see M+4. Okay. Right, so mass spectrum of chlorine. Chlorine has 2 isotopes, chlorine 35 and chlorine 37, in the approximate ratio of 3:1. So that means 75% and 25%. You have 75% chance of finding a chlorine 35 compared to finding chlorine 37. So the more abundance or the more common isotope of chlorine is the chlorine 35. Okay, but we cannot just ignore and say, oh, just because 37 chlorine is not common, so we're going to ignore them. No, because sometimes naturally they are present and we cannot avoid them. So you may think that the spectrum would look like this. There's a signal at 35, which represents 75% because it's 3:1, right? I hope you know how to turn your ratio into percentage. And for the chlorine 37, the relative abundance is 25. Or another way of seeing it is that if you take the height here, okay, it's 3 times, chlorine 37, chlorine 35 is 3 times of chlorine 37. That's how you see 3:1. For me, I like to look at percentage. I don't really like to look at the ratios, but you can see that this is each line represents the 25%. So there are 3 times of the 25% in the chlorine 35. Okay. Okay, so the problem is that chlorine consists of molecules, not individual atoms. So when chlorine Cl2 is passed into the ionization chamber, an electron is knocked off the molecule to give a molecular ion Cl2 plus. So when we deal with chlorine or bromine later on, you see they don't exist as the atom because the atom is crazy. The chlorine atom and bromine atom are radicals and they are crazily reactive. Okay, so you have to take into account of the molecule of chlorine and molecule of bromine. So that means you also have a molecular ion. Okay, what happens? Same thing. When you introduce chlorine Cl2 or bromine Br2 into the mass spectrometer, two things can happen. The first one is the molecule of chlorine and bromine or bromine can be bombarded with high energy electron, and one of the electrons is being removed from Cl2. That means your Cl2 will become Cl2 plus. This is your molecular ion. Another possible scenario is also is when your Cl2 is being broken down or being fragmented. So fragmentation does not only occur in molecules, but it also occur in chlorine and bromine molecules. Well, because they are molecules, so there is a bond that can be broken between them, the Cl-Cl bond. All right. So when you put chlorine Cl2 molecule in the mass spectrometer, you would expect to see Cl2 plus or fragmentation into Cl plus, right? This is fragmentation. You're breaking down the molecule, but of course it has to be positively charged. If it's the radical or neutral, then it will not be picked up by the detector. And the first one is the formation of a molecular ion. All right. Okay, so your chlorine spectrum actually looks like this. Okay, so let's talk about the easier peak first. Okay, that looks to me like it's a 3:1, 3:1 ratio, and that should be a hint. The ratio 3:1 is for chlorine 35 to chlorine 37. And as a matter of fact, this at 75% is produced by chlorine 35, and then at 25% is produced, oh sorry, it has to be positively charged, okay? It's produced by chlorine 37 with a positive charge. Okay, I think we're all okay with that because, and the percentage would be 25%, 75%. Or if you like to use ratio, you can say that this is 3:1. Okay. Next is you see these three peaks, okay, at 70. Sorry, where are the three peaks? 70, 72, and 74. Okay, so 70, we start with 70, is actually the molecular ion formed between chlorine 35 and chlorine 35. How do I know that? You add 35 plus 35 is 70. The other peak is at 72, is a combination of chlorine 35 and chlorine 37 plus. Okay, you need to write down the plus there. And this will produce a peak at 72 because 35 plus 37 is 72. And lastly, you have this chlorine 37 plus chlorine 37, which adds up to 74. And don't forget your charge. The relative abundance is not the same as you would have with a single chlorine atom. Okay, if you have a single chlorine atom, the relative abundance will be 3:1. However, when you have two chlorine atoms, the relative abundance will change to 9, 6, and 1. So we write the ratio as, I don't have space, 9 to 6 to 1. So the most common species that you will find is the combination of chlorine 35 with chlorine 35. Whereas the least common combination you will see is chlorine 37 and chlorine 37. Okay, so how do I label this in terms of M? Okay, so my molecular ion is actually this chlorine 35 and chlorine 35, right? I then have my next line or my next peak is at 72. So the difference between 70 and 72 is 2 units, correct? So this is called M plus 2. The next peak is 74. The difference between 74 and 70 is 4 units. So it's the M plus 4 peak. Okay, where M stands for your molecular ion, and the molecular ion is your chlorine that is made up of chlorine 35 and chlorine 35. So here you have the zoomed in version, 9 to 6 to 1. How to see this? Well, I'm not great at drawing this. So that's 1, 1, 2, 3, 4, 5, 6. Okay, so there are 6 times of this line. Okay, whereas the 9, I will try 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there are 9 times. That's why the ratio is 9 to 6 to 1. Now, if we convert this into a percentage, it will not be a nice percentage. That's about 9 over 16. Okay, 9 over 16, 6 over 16, and 1 over 16%. So the relative heights of the 70, 72, and 74 lines are in the ratio of 9 to 6 to 1. So whenever you have 2 chlorine atoms, always remember this ratio, okay? 9:6:1. Whereas if you only have 1 chlorine atoms, the relative abundance ratio is just 3:1. And you have to remember which one is the more common isotope, okay? Right, I hope that explains. The text here should be able to explain to you what is producing the signal. I will zoom this in so you can have a look. Understanding the notation is also important because it can tell you, it gives you a hint. If there is a difference in 2 units from your molecular ion peak, that means either chlorine or bromine is present. But you also need to look at the relative abundance. Is the height reasonable? Okay. Okay. Next is, now we're going to look at organic compounds containing chlorine atoms. First, we start with containing 1 chlorine atom in a compound. So if you look at this is of 2-chloropropane. Okay, so I'll just draw out the structure of 2-chloropropane, which looks like this. Okay, so if you take the MR of this molecule, it should give you this value, which is your M plus value. Okay, I don't think is the MR given 78. Yeah, 78. So let's just check. 12 times 3 carbon plus 2, 4, 6, 7 hydrogen plus chlorine. Okay, the question is it chlorine 35 or chlorine 37? Now choose the more common chlorine, which is chlorine 35. So I'll take 35, 78. So the MR is equals to 3 times of carbon plus 7 times of hydrogen plus 35 of chlorine. Now you may ask, why did I take 35? Because it is the more common isotope of chlorine. Okay, so my M+1 peak is caused by this molecule with a positive charge. Okay, and then you see there is a peak beyond my M+, and the difference in mass is 2 units. So that means this M+2 may have been caused by this other molecular ion, but +2 because the difference in chlorine 37. Okay, so if you find the mass, the MR of this molecule, 12 times 3, 36, 36 plus 7, 43, plus 37 is 80. Okay, so that's a hint. If you have 2 peaks at the end of your x-axis and the difference in unit is 2 units, sorry, and their difference is in 2 units, that means either chlorine and bromine is formed. If the difference is by 1 unit, it's the carbon 12 and carbon 13 isotope. So you have to be careful. Now, another thing is that I want to look at the relative abundance. How do I know if it's the bromine or the chlorine? Okay, so if you look at this 2 peaks, the M+ peak, the N and the M+2 peaks, their relative abundance is about 3:1. The heights are about 3:1. Okay, so obviously this is 3, this is 1. Why do I use the 3:1 ratio? Because I've only got 1 chlorine atom. If I've got 2 chlorine atoms, then I will use the 9:6:1. Okay, so there are other signals in this mass spectrum that I don't have to worry about. However, this diagram is highlighting the peaks at 63 and 65. Now, those peaks are produced when you fragment this molecule at this bond. Okay, I don't know if you can see that. It's the fragment on the left where you have 2 carbons. So that's 12 times 2, 24 plus 4 hydrogen, 28 plus 35, 63. Okay, so this fragment is causing the 63 peak. Now there's another peak at 65. So there's a difference in 2 units. So that's a hint that this peak is caused by the isotopic chlorine. Okay, so let's have a look. At 63 is being produced by CH3Cl35, positive charge. Okay, whereas at 65, maybe I'll use a different color. Whereas at 65 is produced by the same fragment, but the only difference is the chlorine is now chlorine 37. Okay, so oh, I've missed out a hydrogen there. Chlorine 37, positive charge. Okay. So the explanation for that is given in your notes. Okay. So if you want to copy this down, again, the relative ratio is 3:1. Okay. Now, when I say relative ratio, you're only comparing the 2 peaks, right? You're not comparing the peaks between the other signals, right? Only focus on these 2, and you can see that their relative ratio is 3:1, 1, 2, and 3. Okay. Right, screenshot here, and I'll move on to the next part. Even the fragmentation is shown to you in your notes, okay? But it's probably not as obvious because it's in the structural formula. Now you can draw out the displayed formula and just show the fragmentation. Okay, don't worry about this plus sign and the dot. I usually like to start from the neutral molecule, okay? But in reality, it's the fragmentations are formed from the molecular ions, but it doesn't matter as long as you label it correctly, okay? Only positive species will produce, I forgot my positive charge here. Also, I left out a hydrogen. So this should be positive charge, okay? All right, moving on. The two chlorine atoms in a compound, which is M+, M+2, and M+4. I believe there is a typo in your notes. The M should be M+ because the molecular ion has a charge, which is +1, okay? Everyone else have a charge of +1 as well. The +2 and the +4 is just telling you the difference in mass between the molecular ion and that species. Okay, so this is the molecular spectrum of a 1,2-dichloroethane. So I will just focus on these three peaks. All right, I will not focus so much on the other signals produced in the spectrum. So let's see. CH2, CH2, Cl. So I'll start with drawing out the molecule so that, okay, the most common isotope is chlorine 35. So that means the most common molecule is also made up of both chlorine 35s, and the mass for this is 12 times 2 plus 4 hydrogen plus 35 times 2. And this should give me 98. Okay, so if you want to label this is 98. The middle one is 100, and the lowest peak is 102. Okay, so this molecular ion is causing my M+1 peak. What is causing my M+2 peak is still my molecular ion. However, the only difference is in the chlorine atom. So difference in two, one of them is the chlorine 35 and one of them is the chlorine 37. And if you're not convinced, you can count again. The mass carbon is 12 times 2, 24, okay, plus 4 hydrogen, that's 28, plus 35 and 37 chlorine should give you 100. Lastly is my M+4. It's still my molecular ion, but now the chlorine isotopes are the most rare, okay, the least common one, 37 and 37, okay? So to calculate this, 12 times 2 is 24, plus 4 hydrogen, plus 37, and another 37, you should get 102 as your mass to charge ratio, okay? Now, when I mentioned earlier, when you have two chlorine atoms, the ratio of the relative abundance is different from when you have only one chlorine atom, okay? When one chlorine atom, you have a ratio of 3:1, as we have seen earlier on. Now, since we have two atoms in this molecule, it is 9, 6, and 1. So it follows the ratio like if you had Cl2 molecules. Okay, so this doesn't matter in what type of molecule you are, as long as there are two chlorine atoms in there, the relative abundance will be 961, and the difference will be +2 and +4 of your molecular ion. You may read the explanation in the text, okay, of your notes, but that should explain the three peaks and why they are at those heights, okay? I'm going to move on. Oh, please spot the typo. There should be a plus sign together with your M. Because if it's not charged, it will not be detected and the signals will not be produced. So it is important for you to write down the positive charge. Okay, moving on to the next one. Effect of bromine on mass spectrometer. So we're going to deal with one bromine atom first. Bromine atom in your periodic table has a mass or a relative atomic mass of 79.9. Okay, so it's a decimal place. That means it must have contained isotopes as well. And as a matter of fact, bromine has 79 bromine 79 and bromine 81, and both of them are equally common. Okay, of course, one is more than the other, but not by so much. I don't remember the 50.5 to 49.5%. So they're almost 1-to-1 ratio. Okay, and if you notice, the difference between 79 and 81 is also 2 units. Okay, so you have to be careful because chlorine will also give you a difference in 2 units. Bromine will also give you a difference in 2 units. However, what differentiates them is the percentage of relative abundance. In chlorine, when you have one chlorine atom, it's 3:1. When you have 2 chlorine atoms, it's 9:6:1. However, for bromine, when you have one bromine atom, it's 1:1. And when you have 2 chlorine atom, two bromine atoms, that means you have your M+, M+2, and M+4, it's 1:1 compared to chlorine 9:6:1. Okay, right. So this is the mass spectrum of bromoethane. Okay, so you've got a CH3, CH2Br. So the M+, since your molecular ion is the lower mass, okay, it's lower by 2 units. That means it is produced by the lighter bromine, okay, which is your bromine 79. So if you count the mass, 12 times 2 is 24, plus 4 hydrogen plus 79 bromine, you should get a peak at 107. Is that correct? 108. Sorry, I must have. That's why, because the next one is 110, so that means it must be 108. 2 units difference. So where did I go wrong then? 12 times 2, 24 plus 5 hydrogen plus 79. Okay, 108. So that is caused by the bromoethane with 79 bromine, whereas the peak at 110 is caused by the same molecular ion. However, the difference is in bromine 81. So we don't call this M+, we call this M+2 for the reason because the difference is in 2 units from your molecular ion. Okay. The ratio is almost 1-to-1, right? It's not exactly 1-to-1. They're not of the same height, but it's almost similar. So that's when you know this molecule contains a bromine atom. So far, we know the identity of the molecules. That's why it's easier for us to assign the signals, okay? But there are cases where we don't know the molecules. However, we're given the spectrum and we are expected to work out the structure. So that's when it gets difficult. Okay, that's that. Next is if we have 2 bromine atoms, as mentioned just now. When we have 2 bromine atoms, the relative abundance is in the ratio of 1-to-1. Okay, so you've got here M+ peak is 1, height of 1, and then M+2 is height of 2, and M+4 is height of 1. So I don't know what molecule this is, but I know that this would have been caused by bromine 79 and bromine 81. M+4 would have been caused by bromine 81 and bromine 81, whereas M plus peak would have been produced by bromine 79 plus bromine 79. Okay, but 158, because this is the mass spectrum of a molecule, so we don't know what the molecule is. Okay. Sorry. Question 6.1. Sketch the overall pattern of peaks in the mass spectrum of molecular bromine. Okay, so they want us to sketch the spectrum for bromine Br2 molecules. Okay, first I will deal with the Br2 molecules first. Okay, where you have M+2 and M+4. So my x-axis will be mass to charge ratio, and then I know that their units or their difference would be by 2 units, and I know that their relative abundance will be 1, 2, 1. Okay. The values. This is my M+1 peak, and this would have been caused by the lighter bromine, 79 and 79. And if I add that up, it's 158. Okay. Next is M+2, which is, sorry, forgot the plus sign. I'll use a different color now. Is now red. Okay. Is caused by Br, oops, 79 bromine and 81 bromine. So that would add up to 160. So you can see already, right? The difference is mass is 2 units. And lastly, if I use blue, is the M+4, which is produced by, forgot my positive charge, right? It's red. And the last one is blue. Okay. It is produced by 81 bromine and 81 bromine. And if if I didn't have a calculator with me, I know it should be +4 from my molecular ion. So 158 plus 4 is 162. Okay, so that's when I have 2 bromine atoms. I must not forget that my bromine molecule can also be fragmented, can be broken down, right? When I have 1 bromine atom, I should have 2 peaks. The difference is in 2 units, and their relative abundance is the same, 1 to 1. Okay, so I'm just going to make up the numbers here. So I've got a peak that is caused by bromine 79. So obviously it would produce a signal at 79. And I've got another signal for bromine 81, which would have produced a signal at 81. And the ratio is 1 to 1. Whereas for 2 bromines, I have ratio of 1 to 1. Okay, so don't get confused with my 1 to 1 ratio, and 1 is to 2 is to 1 ratio. Okay, right. So do I have space for this? Okay, so I'll just add on last few things here. Bromine is a diatomic molecule. Don't forget to label your y-axis. So there will be 5 peaks or 5 signals on the mass spectrum. Okay. Okay, so this is the fragmented, whereas this is the molecular ions. Well, actually the molecular ion should be M+, not the M+2. Okay, maybe I should change this so as to not confuse you, right? Molecular ion is the one at 158. The 160 and 162 is just due to the isotopes of bromine. Okay. All right. So I will stop here and I will continue with the examples in the next lesson. Okay. As usual, please don't forget to fill in the questionnaire in forms, and that will be your attendance. Assalamu alaikum, and thank you, everyone.